Welcome to the Explainer. Today, we're demystifying a seriously complex technical tutorial on how to build a multimodal reinforcement learning pipeline, step by step. Look, if you're building next-gen AI, you already know the deal. Teaching models to actually reason instead of just confidently hallucinating some completely fabricated answer is literally the frontier right now. So we are going to unpack exactly how to set up a pipeline that evaluates and trains those models with absolute precision. So, how do we teach AI to actually verify what it sees and reasons? Getting vision language models to accurately process images and output verifiable math or logic is honestly a massive challenge. I mean, we've all seen an AI confidently spit out the completely wrong mathematical proof after looking at a super simple chart, right? But the Turing Enterprises/Open MMRL dataset gives us the absolute perfect foundation to solve this. It hands us the raw materials to make sure our models aren't just guessing, but actually proving their work. Okay, let's define RLVR. This is the core concept behind teaching our AI to accurately grade its own complex answers. RLVR stands for reinforcement learning with verifiable rewards, and it completely shifts the paradigm. Instead of relying purely on, human vibe checks or soft preference data, we use objectively verifiable answers. Think about it. If the AI is asked to solve a geometry problem, the math is either right or it's wrong. RLVR leverages that exact objective truth to reward the model, which accelerates its reasoning capabilities exponentially. Think of this explainer as a giant factory assembly line. Here's our blueprint. We're going to cover the multimodal AI challenge, loading the raw data, analyzing the dataset, building the reward grader, and finally exporting the RL pipeline. Let's kick things off with part 1, the multimodal AI challenge and structuring the journey. Look, before we write a single line of code, we really need to map out exactly how information will flow. You wouldn't build a house without a blueprint, right? So we have 4 main stations on our assembly line to ensure our data is perfectly prepped. First, data extraction and inspection. Second, exploratory data analysis, or EDA. Third, reward scoring, building an uncompromising automated grader. And fourth, GRPO export, formatting everything so our RL algorithms can consume it flawlessly. Moving right along to part 2, loading the raw data using the OpenMMRL dataset. All right, let's look at our first concrete step, bringing in the raw materials to fire up this assembly line. We start by installing required libraries and importing our core tools for dataset loading, analysis, and symbolic math. Then we set random seeds. This is a small but absolutely crucial step for reproducibility. You want your experiments to do the exact same thing every time. Trust me, it'll keep you sane during debugging. Then we load the Turing Enterprises/OpenMMRL dataset directly from Hugging Face. We immediately inspect its size, features, and peek at that first row structure, just to ensure our data perfectly aligns with our expectations. Next up, part 3, analyzing the dataset through exploratory data analysis. As you probably know, raw data is inherently messy, so our next step is sorting and inspecting it to truly understand the schema. We convert our dataset into a data frame, but here's a quick pro tip. Temporarily remove the image column during this step so you don't completely blow up your memory. Doing this lets us rapidly calculate some vital statistics, like the total number of images, how verbose the questions are, and the exact answer lengths. This is super important because it tells us exactly how much context window our vision language model is going to need later on. Visualizing the dataset's composition is absolutely crucial. We break down domains, subdomains, and various image formats to make sure our model's training data isn't skewed. Think about it. If 90% of our data was geometry and only 10% was algebra, our model would completely overfit on shapes and just fail miserably at equations. So this visual step essentially guarantees we're training a well-rounded reasoning engine. We also do a manual visual inspection step. We want to display one representative example from each domain to really understand how these multimodal reasoning problems are structured in the wild. We get to see the exact question, the associated image, maybe a complex chart or geometric figure, and the gold answer that our AI eventually needs to match. It really brings all that abstract data down to a tangible reality. Okay, part 4, building the reward grader to verify those complex answers. With our data fully understood, we arrive at the most critical machine on our entire assembly line, the reward function. This is literally what makes the verifiable part of RLVR possible. Here's the thing. A rigid text comparison against a gold answer will absolutely fail on complex math. If the gold answer is the fraction 1/2 and your AI outputs 0.5, a rigid exact match grader marks it wrong, which completely ruins your training. That is exactly why we build a symbolic match grader using a LaTeX to SymPy converter. It transforms flexible string text into pure mathematical logic so we can evaluate expressions reliably, totally regardless of formatting.
This verifiable reward function acts as our ultimate quality assurance check. It has some serious capabilities. First, it extracts the final answers, which are usually buried at the very end of a long chain of thought. Then it checks for exact matches, numeric matches, fractional matches, and even checks LaTeX and symbolic answers. If the AI writes some crazy complex LaTeX fraction that mathematically simplifies to the correct answer, our grader is smart enough to be like, yep, that's right, give it full credit, and issue the reward.
Moving to part 5, prompting and model inference. Time to test the logic. So before we export everything, we need to check our work. We format our prompts to force the vision language models into a strict reasoning pattern, and then we run a quick sanity check to ensure our brand new grader actually works in practice. We check our CUDA availability, and then optionally run a lightweight model like small VLM on just a few sample examples. It generates predictions, and we score them right there with the reward function. Seeing this work end-to-end proves that our logic is totally sound. And finally, part 6, exporting the RL pipeline, getting it ready for training. Our data has finally reached the end of the line. It's ready to be packaged up for the AI's rigorous reinforcement learning phase. We export the dataset into a GRPO-style JSON-L format. GRPO stands for Group Relative Policy Optimization, and let me tell you, it is the absolute holy grail for multimodal RL right now. Instead of just rewarding the AI for being right, GRPO evaluates a whole group of the AI's answers against each other, rewarding the ones that are relatively better. But for this advanced training to work, the structured layout has to be absolutely perfect. In this final stage, we go through a few key export steps. We save all our processed images physically to the disk so the training loop can fetch them instantly. We finalize that GRPO-style JSON-L format, and we even demonstrate some mock GRPO rollouts. We calculate group relative advantages right there in the code. This lays out exactly how this placeholder logic is going to be replaced with real, model-generated samples once you kick off your massive training run. This entire workflow takes us from basic dataset loading all the way to LaTeX-aware answer classification and GRPO-style rollout preparation. As the source material highlights, quote, it provides a strong starting point for training and evaluating vision language models with verifiable rewards, while also helping us understand how to transform multimodal datasets into practical reinforcement learning pipelines, end quote. It essentially bridges that gap between raw, messy data and a finely tuned, mathematically verifiable training loop. As we wrap up this explainer, it leaves us with an incredibly exciting and maybe slightly intimidating thought about the future. With pipelines this automated, pipelines that can flawlessly grade and verify an AI's complex visual reasoning and mathematical logic without any human intervention, what will multimodal models master next? Seriously, what limits are even left? Thanks for joining me on this deep dive. Keep experimenting, and I'll catch you in the next explainer.